let's take a look at a real-world situation where we can use a system of linear equations to help us find out some information that we want to know. So let's take a look. We have Peter and Paul are going on a trip to Peru this summer. The cost for the trip is $500 per person. Peter can save $100 per month for the trip, and Paul can save $75 per month for the trip. Here we go. So if Paul begins with $200 in a savings account, we want to know these three scenarios. We want to know how long it'll take for Peter to save for the trip, how long will it take for Paul to save for the trip, and how long will it take for Peter's savings account to catch up with Paul's savings account? All right, so very good questions here. We want to graph this to get an idea of what's going on, so we're going to need two equations, one for each person's savings account. Now for the system of equations, we can actually use something very similar to something we've seen before called the distance formula. If you recall, the distance formula is distance equals rate times time. All right, we've used this formula in a few different sections, so we should be fairly familiar with it. Since we aren't necessarily dealing with distance, but an account balance, it's still a linear equation, and it actually looks very similar. We can just substitute a few of the variables. We can say that the account balance for each person, the savings account balance, equals the rate of how fast that they're saving money times the amount of time that they're saving money. So let's go ahead and use this formula, which is very similar to the distance formula, to calculate each person's savings account. All right, and if we want to shorten this, we can just call it B equals RT, balance equals rate times time. And the formula will essentially work the same. So we're simply defining our dependent variable differently, our dependent variable being balance. So let's write a few equations. Let's say, let's handle Peter's equation first. We have Peter's equation, and it's going to look something like this. So we know that Peter can save $100 a month for the trip. If we define T, our time, in months, then we have his balance equals 100 times T. He's saving $100 per month, which is the rate, and T equals time, or is going to be given in months. So this is the equation for Peter's account balance. B equals 100T. Now let's construct an equation for Paul's account balance. So this is Paul's equation. All right, so what do we know about Paul? We know he can save $75 per month for the trip, but he also begins with $200 in his savings account. So his account balance, B, is going to be $75 times the number of months plus 200. So he's going to have a $200 head start on Peter. All right, so we have two equations here, and we can go ahead and construct a graph. So let's go ahead and do that. Oh, excuse me, it needs to be kind of straight. Here's our y-axis, and well, actually we're going to be dealing with just in the first quadrant, because both time and money can't be negative. We're not dealing with a negative amount of time or a negative amount of dollars, so we can just zoom in on the first quadrant. This is our y-axis, and this is our x-axis, but instead of x and y, we're going to label them. This is going to be the balance axis for each person's account balance, and this is going to be the time axis. Time is going to be given in months, and balance is going to be given in dollars. Okay, so let's go ahead and scale this. Let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That should be good. And 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So we have our graph here. We're going to go ahead and label these. Let's go ahead and scale it by 75s. So 75, 150, 225, 300, 375, 450. We're just constructing an old graph for our account balances. This is 600, 675, 750, 825, 900, and so on and so forth. 975. And our months are 1, 2, 3. We're just passing 1 month at a time. 5, 6, 7, 8, 9, and 10. Okay. All right, so we want Peter's equation. We can actually solve by just plugging in one month at a time. So for Peter's equation, when t equals 0, his balance is at 0. So Peter's equation starts here. He starts with no money. After 1 month, he saves $100. So we're just going to graph it like so. It'll be somewhere right about here. After 2 months, he's at $200. And we're going to make this straight as possible. 3 months, he's at $300. At 4 months, he's at $400. At 5 months, he's at $500. Just somewhere right about there. 600. He's at 600 at 6 months. At 7 months, he's at 700. At 8 months, he's at 800. And you kind of get the picture. Okay, so let's go ahead and connect. This should go through all the dots. The line should go through every single dot. So we'll just kind of imagine that this is some sort of a straight line passing through all the points. And this keeps going on just in case he was saving forever. All right, so this is Peter's equation. We have Peter's equation right here. So this is Peter. All right, let's go ahead and see what Paul's looks like. Paul's equation at time 0, t equals 0, it's going to equal 200. And this makes sense because he has a beginning balance of 200. So he's going to start at right about $200, or $200 is right about there. After 1 month, it's 200 plus 75. So he's adding 75 to each month. So 275. At 2 months, he's at 350. At 3 months, he's at 425. Oh, should be right here, excuse me. This is the most tedious part of doing a graph, is actually plotting the points sometimes. At 4 months, he's at 500. At 5 months, he's at 575. At 6 months, he's at 650, which is right about there. At 7 months, he's at 725. And you can see that the two equations are converging. At 8 months, he's at 800. Okay, and that's actually 800 right there. So let's go ahead and connect the dots. The two important points are the first one and the last one. All these should be on the line, but the most two important ones are the first one and the last one. All right, and this is Paul's equation. This is Paul's savings account. Okay, so we want to know how long will it take for Peter to save for the trip. So what we want to know is when our balance, we know he needs to have $500 in his account for the trip. So we want to know what Peter's equation equals to when B equals 500. We want to solve for T. So for Peter, we're going to have 500 equals 100T. We want to solve for months for T because we want to know how long it takes for him to save for the trip. So let's go ahead and divide both sides by 100. You can cancel out some zeros here. And we get T equals 5. So it's going to take Peter 5 months to save $500 for the trip. And this is the graphical representation. At 5 months, Peter should be right at $500. All right, so this is his point at 500 where he's able to afford the trip. And it should be right at about 500. Okay. Not exact, but you get the idea. This is just a graphical representation. Now we want to know how long will it take for Paul to save for the trip. This is A. This is the point A that we're looking for. So Paul's equation, we want to know when this side equals 500, when its balance is 500. All right, so 500 equals 75t plus 200. We want to solve for t, so let's go ahead and do so by subtracting 200 from both sides. Those two terms cancel, which gives us 75t equals 300. We can go ahead and divide both sides by 75, isolating our variable t, which t will equal 300 divided by 75 is 4. So it's going to take Paul 4 months to save for his trip. So at 4 months, Paul is at 500. All right, they're getting there at the same point at $500. Just Paul's doing it a month early. So that's B. This is the point B. All right, now the third question is, how long will it take for Peter's savings accounts to catch up with Paul's? All right, so in essence, what we're asking, and we can clear a little space here if we're done with this, we want to know the value of t, how long it takes. We're talking about time. We want to know the value of t that when we set these two equations equal to each other makes them equal. So if you look at it, if b equals 100t, regardless of who equation is, b equals 100t, well, we can substitute in 100t right here for b, because we know b is equal to 100t. So it's my argument that we could do this. 100t is equal to 75t plus 200. We just substituted 100t in for b because we know they're equal. So mathematically it makes sense, but if you think about it, we want to know when these two lines, or these two equations, are equal to each other. We want to know where they intersect. And that's what we're trying to learn here when we're talking about solutions to systems of linear equations. We want to know where they intersect. We have a good idea where it happens here, but we want to know the exact solution. So what we're going to do is we're going to set both equations equal to each other and solve for t. Well, we know how to do this. We've been doing it all along in this course. So let's go ahead and subtract 75t from both sides. We want our variable on the left-hand side and everything else on the right. So we have 25t on the left-hand side equals 200. And we can isolate our variable of time by dividing both sides by 25, which gives us t equals 200 divided by 25 is 8. So we know that at 8 months, Peter and Paul's equation equal each other. So if their equation is given as a balance, we know that their balances are equal. So right here at 800 is going to be, at 8 is going to be the the number of time where our equations are equal. Mm-hmm. So if we want to know what the actual amount is when they're equal to each other, which we're not asked here, but let's go ahead and take another step, go the extra mile. We can plug in 8 in for t. So if we do that here, b equals 100 times 8, which is just 800. So we know that at the point 800, that's when our equations are equal. And see, we're a little bit off on the intersection here, but not by much. This is actually, we were talking about when we're graphing systems of linear equations, the actual graph is just going to be an approximation of the solution for the system. All right, so it's where they intersect is the actual exact solution, and we're just a little bit off, but we know that after 8 months, both Peter and Paul's savings account, their respective accounts will be equal each other, and they'll actually both be at $800. So this is very useful information that we can use when not only just saving for trips, but in all of business and finance. We can use this to actually construct business reports and future earnings and such. So be sure to go over this again, get a really good handle on this, because this is actually a very useful application when solving systems of linear equations. So I'll see you soon.